lecture, the second part. So now I come to what I would like to consider here. This will be the end of the talk. I don't know whether it will be today or tomorrow, but you see here I have the smallest test space of Lumiere type, and this is the smallest space of Ionic type, which I will define later, and try to do what one can say about inverse closedness within symbols in that space. So this is some kind of subject of the paper. Here I see this second paper, so I just repeat as we usually do in phase space. We have this kind of notation. We have this weight. I mean, for V, we have this kind of submultiplicity, and then with this V, we define the weights. And after all, this is just theoretical part. One just have to remember that I will consider such kind of weights, and this is Japanese bracket, as Boyan told. This is interesting. I heard for the first time for that Japanese bracket from Krzyzanski. When he told this, let me say, a long time ago, we were laughing, but he said this is in Japan. It's Japanese brackets, so we take this name for that. It will be clear what I do. This is Fourier transform, different than what this one, what Boyan used yesterday, what Hermander one. But this one is even simpler. This is what Lerner and Bonny and other French mathematicians use, because there are no constants in front. There are many discussions of that kind. And so this is space which I already told, just a repetition, basic. We start with this, and you see, if I take union, then I can have S equal 1/2. But if I take intersection, I can take S to be strictly greater than 1/2. And so they are with very well known topology. This one is DFS space, this is FS space. And so these are very well known facts about density. So always Ionic space is included in the Lumiere space, but only for S equal to 1/2. Even in that case it is true, but then the only case is just space which contains 0. So and this S 1/2 is actually the smallest one. And so here I defined actually, there are many results of mine, all the results in 80s, 90s, last century. And Toft is now working on that, and his students, he has really, even in the last paper, he go beyond the S 1/2 and explain all these spaces with the fractional Fourier transform. And so there are many old methods used for the analysis of such space, but I define this one as here it is written. For me, of course, this is product of harmonic oscillators of one-dimensional. Everything, of course, can be done with n-dimensional harmonic oscillator, d-dimensional harmonic oscillator, but I prefer it because I did this with 81, something like that. So many years ago, in more than 40. So these are what is missing here is Hn. These are eigenvalues of operator r to the power k, and here you should have Hermite function, which are just products of one-dimensional Hermite functions, so everything works well. So this is well-known space. I mean, somehow interesting to some people. And so we know that this now tilde, which is not empty, is just dense substance of that one. But you know, S1 half is defined by the differentiation and product with polynomial, as in the case of Lumiere. And here, this one was defined by harmonic oscillator. So this is the main difference how I came to that space. So, because nothing can get if you try to define that space by using differentiation and multiplication by polynomial. So this will become later in the field of my talk. Now here I wanted to explain this because I expected that that Bojan will talk about another paper of us about harmonic, about pseudo-differential operators in harmonic analysis, which actually this was origin of the problem, which I discussed with Bojan, and then Bojan said, why we should do this in some special case, let's do this in Hermander calculus. And so this is really, I don't know, he will not talk about that, so maybe we will see, maybe tomorrow I say something about that instead of what I planned. So what is again repeated here, so we have this sequence space, and what I already told to my young colleague. So when you have space with index s, then sequence space which corresponds to it has index 2s. So if you have s equal to 1/2, then this is actually a r to the power 1. And this is the most interesting case. And again, this is just a repetition of that space of sequences with this kind of norm. And this is algebra under convolution, usual convolution of sequences. And we have, this is actually Toft notation. He put 0 for those which are Jordan case and for those which are Lumiere case. Just the same symbol, but here 0. In my opinion, it's okay. Everything is fine for me. So here, as I told, this what one has working in sigma tilde, then one comes to that A01. So somehow, from the point of view of sequences, you do not feel this difference, what you did on the level of spaces. On the level of sequences, you just get quite normal relation with s equal to 1/2 and s greater than 1/2. And actually, this is what Toft did. He goes beyond s 1/2, and he introduced many things later with this. Okay, so again I repeated this what is p of x. This is just package translation and modulation, because with this we will make Gabor frames later. This is again written in another form, short-time Fourier transform. Of course, we also did some work with, if you take instead of Fourier transform, if you take short-time Fourier transform, then you will come to so-called anti-Wick calculus, which is also important because positivity is of symbol just gives you positivity of the pure differential operator. But so just a small remark on that level. And so what we will use later, this notation, this is Wigner transform. Actually, this Wigner transform probably is the most important transform. Everything comes to that. To that transform. It's defined here, but this is defined in so you see, you have dimension is different. Dimension is different, so you have r to the power 2d. Usually we have here f of x minus t half, f and h of x plus t half. And I wrote this version because if you just cancel second variable, you get this classical Wigner transform. And so, but in this form, one can simply arrive to so-called Bachmann transform. So for me, Bachmann transform is which connect Bachmann spaces with function spaces over Rn or R2n. So this is done in that way. There are some other on that place you have. Here I is missing. I see now. I should be written here. Sorry for that. So this is about the knowledge which I should have. Again, repeated the definition of modulation space, and because somehow what people of time frequency use, they use this space M11 as the smallest one for the source of window function. I mean, when I look this function h or g here, this is called window function. So somehow for that function, usually they use this M11 with some weight. So somehow I wrote maybe what one should remember, and already I will tell sometimes that instead of g I can take another function, but this is just Gaussian. And Wigner transform of GG is again Gaussian, but with here is minus pi, and here is minus pi half. So these are technical results which are somehow important. But the relations of wave quantization of a symbol, which is here in S to S prime. This now S sometimes is up or down, but it depends what I put. I forgot sometimes what I put before. So so there is a relation which we like very much. Actually, this is the basic relation between wave quantization and short-time Fourier transform. And you see that here we use this V retro on the 2D dimensional version. And so if you just make a change of variables, you come to that relation between. Now you have this side on the left. And you should remember j of x psi, this is psi minus x. Yesterday, this was what actually symplectic transform do on vector x, xc. So xc goes in front. If you write down symplectic product, you can see simply that j is very much connected, and some people do not use, let me say, this symplectic form of Fourier transform. They use this but with this operator j inside. So in any case, this is well known. Again, now I'm talking about Gabor frames. In the previous talk, this was a frame, in some sense, general frame, but now we would like to speak about Gabor frames. So again, I repeat the inequality for the frame, and here it is type frame, which I already told at the beginning of my talk today. So everything is written here. And then in Hilbert space you have this well understand development of F by frame and the dual frame. And some people just use Gabor tight frames, but this is really not important. Here is definition of Gabor frame. So you have to, what does it mean on G? This is actually G of x minus, so I didn't write what is P. P of lambda, let me say, if this lambda 1, lambda 2, this is in two-dimensional, 2D variable. So there, lambda is lambda 1, lambda 2, and then you have to make a translation by lambda 1 and a modulation by e to the power 2 pi I lambda 2 xc. So somehow, probably later this will be written more carefully. And with this, you have again this kind of expansion, and what we discussed on the break. So, what are the best Gabor frames? This question was written by this school of time frequency analysis and discussed in many papers. So you see that one can start with just with the first Gaussian or first function of Hermite expansion, H0. Let me say this is H0, how it is written here. And then if you make a frame in that way, dual frames still satisfy the same, not with the same constant, but you see that both, so gamma tilde, this is gamma hat has the same kind of estimate, because you already know that this has this estimate. And so somehow this is the best result, how you can use frame. What should be the best frame? Of course, today these people in frame theory or in time frequency, they have already dictionaries, and they don't care about, they use Haar orthonormal system and make frames with Haar, which is just you know what is Haar basis. But in principle, for us, if we do some kind of analysis with find properties of derivatives and so on, so we should have best frames, and this is probably the best one. And so for S, then, so you have this kind of estimates where S is greater than 1. This is also frame for some positive constant. So this is when S is greater than 1. This is this. Later you see this goes 1 over S. So this is less than 1. So this corresponds to beta less than 1. So better choice is that estimate, because this estimate corresponds to S equal to 1/2. Reverse it. So you have again UG. This is analysis operator and this synthesis operator, and so then all the things are the same in that theory, which is quite nice. And then, so now I will explain these spaces which are now used for our as an introduction. Still, this is introduction for results which will come later. I don't know. I have to finish it for half an hour. I will see how much of that I will tell. So this is Wiener type space. Probably in harmonic analysis you should know how it is prepared, how it is constructed. So you have function, and then you have C should be some open bounded set, as it is written here, and then you just make translation with lambda, and you consider supremum. Of course, there are Wiener type spaces which correspond to LP norm. This one corresponds to supremum norm. You see, and so this is, and then when you do this, then you have you get sequence F lambda, and Wiener type space, which depends on that, is just what is written. So if this quantity makes a sequence which is in ASR, whatever ASR, so you just look at as exponential case. This is for me only interesting. And so now you see this is version of symbol class, and somehow not so easy. You should write this quantity, which is what is G sigma. One should start from that side. G sigma is just this quantity, you see. This quantity is G sigma. It's already complicated to write down up to that. So this is G sigma. And J is just this, what I repeated the notation, just reverse these variables with minus on it, on the first one. So this was Y, and this is J of Y. And so somehow this is a set of symbols. When Stevan did it, then for him this is just infinity, and here this is, instead of this sequence he used L1. That's the sequence of convergent series. And so, and then Grökening and his collaborator did this in a more general setting, and what I wrote down is just introduction, and I will explain this for projective and inductive limits of such spaces when R tends to 0 or R tends to infinity. So this is the subject of what is going on. So here is written again, so this is the set of symbols. Symbols are in that class. This is modulation space. So if it is modulation space, you do not have differentiability, and so the symbols are not smooth. You can somehow play with the derivatives. This is actually what I thought was important for that people. And so, as Shestrand did for one infinity, Krekling did for that space A, and what I'm putting in this introductory part is just instead of A, I consider families of sequence spaces, and then I will later in a minute consider a projective and inductive limit of these spaces. For this is just one of conditions, because as you remember, everything can be done by phi as Gaussian in 2D. But if psi satisfies this kind of condition, that all the quantity which is written here belongs to that Wiener type space, then you can do everything with psi. So somehow this is technical part, but okay, this is just a fact, nothing more. And maybe I will not repeat this. This is somehow difficult to prove, but sometimes it's important that your theory does not depend on the window. And so now I did this as projective limit, as inductive limit. So this is Wiener type space, an inductive limit of Wiener type spaces, with all the good properties which I will not tell anymore. And so you have this kind of grand symbols defined in that way. And so this is actually space, inductive limit of modulation spaces. And the same thing was done for I think, yes, this is still on A to S. Remember, A to S is just inductive limit of spaces A to S R. And so this is space of symbols, which I already told. And so I call it graded algebra, this A to S. And fresh algebra is obtained by this. Probably this is on the next slide, not on the previous. Yes, this is here when R tends to infinity of these kind of spaces, and then you have some properties that you should use for the window. This is not so much important in this moment. Let me just repeat that this space is projective limit of modulation spaces. For some reasons, we always look on that kind of spaces, because in the function space we also consider projective and inductive limits, and there is a lot of topology inside, which I didn't tell in this moment. And this is just a repetition. What does it mean that f of y is in that Wiener amalgam space? And so let me skip this explanation once again. And so this is the result. This is the result which was later generalized, and this is somehow for people after 2010 was interesting to, as I told, to Gröhering, Cordero, Rodino, Nicole, all these people. So they show that this quantity. So now you can recognize what I wrote here. This is actually here written. So this is that line. So in discrete case, this is discrete case. So this is completely the same thing because this is for me what I denote by Hn. Hn. And so, but here it is given in the form of even this is with tight frame because on no, it is no. This does not depends. This is always the same. But in the proof they use just tight frames. So you have this kind of diagonalization. You see, and then some kind of I will connect this kind of estimate with almost diagonalization. So, and this is explained here. We obtain that the frame expansion of sigma, the dominant role have coefficients near the matrix diagonal. This is why this theorem gives almost diagonalization. So somehow this is part. This is discrete version of that continuous version, and you see that function h belongs to Wiener amalgam space, and here this is in the secant space which corresponds to that. So these results actually hold in many situations, and here I just collect them. For example, Rodino and Cordero, they did it with A0 just in, let me say, for 2s greater than 2. Nothing, 2s is just greater than 1. But they wrote a paper with this in the book of them. But for me, this is not important. I mean, this is not a big deal to see that this holds also. And so somehow this is the point, and I will not talk about that. I plan to talk about that. Actually, I left this to Boyan, but he didn't. He will not consider that theory. We did this almost diagonalization in Hermander calculus, which is very much different than classical. Huh? So now I go to metrics. So how we will make metrics? So you see, you have, let me see, metrics ANMN, and you make a sequence. You consider, you see, in any row, you consider elements which are of that end of the diagonal on distance n minus n. So this is fixed somehow for n, and then actually you go to such sub-diagonals in that way. And so you make a sequence, AN, and we say that matrix, this family of matrix, that A belongs to that family of matrix, denoted again by A to the power 2s R, if AM formed in that way is in that sequence space. So somehow tricky part how this was introduced, in the sense that actually up to now I didn't use metrics in the whole theory, but now I will use them because you will have a fundamental inequality that what you can prove by using linear amalgam space and this diagonalization, you can do this with estimates on the metrics. And so somehow, again, in both cases, we define inductive and projective limits of this matrix. And so, with topology, which I already noticed. And so we have this notation. So this is sigma VPM of G. This is frame. This is frame. Another. And this is what I wrote here, H and M. Because sequence orthonormal basis is a frame, so I can do this. But in my talk later, I cannot do anything with the so-called general grammar frames. I have to go to Hermite because Hermite functions has their own properties which are very, very, very specific, very good and very specific. So with these matrix elements, we have, so this is frame, as I already denote, maybe not. So what is it? Gj of Gg of lambda. This means that I apply on G my package P lambda of G, and I do this on gamma, and I have dual frame, both are Gabor frames, and so now I'm trying to explain symbols by the use of metrics which I already introduced. And so you see now that you have this kind of estimate. So this is a theorem. So we have this kind of estimate, and now I will use this fact for my own results later on. And so this is the last, so this is just again short time Fourier transform in the version of this P of M. M is, you see, M has two D dimension. And so this is expansion, usual expansion of F, which I actually used here, but I found just coefficients. I didn't write the whole. So in the end, I wrote the whole thing. So this is the same thing. And so somehow, what we have this kind of relations between sigma V of F and this M of sigma. This is matrix, which I defined. Where I defined matrix. Did I go back or here? Down. You see. Sorry. This is matrix M. And so somehow with this, and this is theorem, what you can say about metrics. Actually, this is equivalent to what you told, if you consider, so this, after all, this characterizes this class of symbols. So this class of symbols are characterized by matrices, metrics. And so the last theorem of that kind is just this almost diagonalization, which is written in that line. So you have how it works on a discrete set. You have this. You see, now this is with 2s, which I told you already. What does it mean? So for Bjorning case, this is different, and for Lumiere case, this is different. And so let me repeat the whole theorem. Sigma x maps this space into. So this is weight. I didn't say so much, which means that one is variable, space variable in the frequency variable. This is weight. This one, 2SR. So this mapping is continuous. So if and only if you have this kind of inequality in the Lumiere case and in the Bjorning case. And so this is somehow actually introduction for the results which will follow later in a concrete situation which I already announced. Maybe I will tell you something and tomorrow continue with this. But so these three conditions are equivalent. So you have continuity of pseudo-differential operator characterization by frames and action on frames. This is almost diagonalization because you see that you have here just distance between these two. This is just d of that member of lambda and another one. So with this we have this kind of inequality, and here this is the conclusion. Sigma is invertible, then the inverse has a symbol in m tilde 2s, respectively a0 2s. So this, of course, holds for s greater than 1/2, both part of this theorem. And okay, I will continue. Probably I have time just to finish with this. So for me, the main interest comes from S1/2, as I already told. These are the result of my mod 1, and this is the result of Rengowski, Žigić, and myself about metrics. So here I will tell you what was the assumption on phi. On phi, assumption is that this is a negative function of 0 infinity. This kind of estimate should hold. This is homogeneity of order a minus 1, a is greater than 1. And this is function phi. And some good example of this function is p to the power alpha, or phi of p equal to logarithm of p plus a e plus 1. And so products of such function belong to the same class. So let's see what will come later. So this is the main theorem. Actually, this will come a little later. So if so let us assume this is band limited case. This is repeated band limited case, and this is what I already told, that actually you can not get without assumption on C, additional assumption on C, you can get just epsilon, and you cannot control this epsilon for the inverse matrix. So, so this is actually a problem which I posed to myself, what to do with this constant C. And so, also, as I told, almost at the beginning, d to the power r with r greater than 1 will not give anything new. This just shows the matrix which I presented on the previous lecture. So, and so I will, you remember that I already mentioned that kind of summation. I will use it for n equal to 2, just the notation for the next. So remember that I put here epsilon before and here epsilon, and then it goes to infinity if epsilon goes to 0. So now I fix this quantity, and so this is the main theorem. So if there exists k such that, such constant k such that for every p one has e to the power p phi of p e to the power minus p dst. So now I have my constant which grows together with p. This is what I wanted actually. But somehow, how to control this constant, this was the problem. And so with this, I can say that in that case, I have, for every d there exists cd. Now I cannot control this constant, but I know that for every d there exists cd, in the sense that okay, I started with some matrix with this property, and then with this property I can construct a matrix such that AST to the power minus 1 behave as I would like to have, but without control on CD. So this is the, how to say, from my point of view, most difficult result in that setting. And then I try to explain this on concrete, in the concrete case. So if I take phi this is, sorry, this is 1 prime, or 1, I don't see. So if I have phi in that phi should be in 1/2. This is mistake. So if because I have this development, PHN, and so then I take sigma from that space. Now sigma is symbol. So sigma is now in the, let me say, the biggest class of symbols. Because sigma prime tilde is the biggest space, which is, how to say, bigger than Gelfand-Schilov S1/2, 1/2 prime. This one is biggest one, and then I did my job as what I did here, how it works. Only instead of, no, it's the same. I put action on HN. So with this, I have got this matrix, and so this matrix is just here. When I have coefficients, I have this sequence, and with this sequence, this is what I denote by the action of A to the power to EAM is Bn. I mean, M. So as I told you, matrix do that action on sequences, and I have this representation where A and N is equal to that quantity. So this is what I wrote on the table. Action of sigma, agent, and AN. It's important that here we have Hermite functions, because I will tell something about Hermite functions a little later. And this is a theorem. If sigma belongs to that space, and if I have this matrix, N, this matrix, then e to the power -1 determines an element of the same space, so that A and N is just, so I have this inverse element, and wave quantization of it. It works in that case as a matrix. So somehow this is proved in several lines. Some details are given, but this is the main theorem. Somehow idea was to consider the biggest, how much I go to that sequence, that matrix, which are estimated by exponential powers of the distance between N and M. And so some answer is given in that theorem, and there are some details on the proof that I have even kernel, which Boyan already told yesterday. Probably I will not say anything about that. Some calculation here, kernel written in that form as usual, and so on. So I repeated, it's just proof that F, which appears here, is really one from that space which produces this kind of matrix, and which means that this is pseudo-differential operator. So for us it is important that we have got pseudo-differential operator. And so this is the definition of that F. Again, I have just put matrix elements on that place, as here I have the same thing. These A and M's are just matrix elements, and so it works in as previously on test function phi and psi, but I should tell where is phi and where is psi. Probably this is given. Is it given in the in that space? Phi and psi belong to that space, and so this space is somehow strange one. This is completely new one, because this is defined, you see, this is defined by the use of harmonic oscillator and by the use of classical definition of Gelfand-Schirmer. So combination, and so even it was somehow important to prove that you can commute these operators. R should come on that place, and this was done. This was done, and this space is defined in that way. This is actually the P product, tensor product of S, as I wrote somewhere on the beginning. This space is a product from P product. This is, I will not say what P product, tensor product, but this is S1/2 tensorized by this sigma tilde. So maybe, yes, this is here. I wrote that. And I will finish with this. G is in that space, and theta is in that space. This is just something which was needed for this relation. What is short time Fourier transform of that quantity? So you see that window function and theta belong to different, and then so theta is in S, and this is in sigma tilde, and window belongs to that. Because of that, I can use what I already told, symbols in S, sigma tilde 1/2 prime of all this. And so, I think this is just appendix calculations, which I will not repeat, and so on. There are many simple things which are, this is just change of order of operator R and operator C alpha D beta, and I will stop here. I will not. Sorry for 5 minutes more. This is what I wanted to say. Thank you.
So thank you very much, Professor Pilipovic. If someone has some question, please, comments. Okay, if not, again, thank you very much. And well, some announcements. We will go to the PhD room to take the sandwiches because it's a little bit bigger. And